Hello everyone. As he said, I am the first local guy here in the conference, so this is my daily working place. I hope you like the environment and you have a nice day here in Malaga with us. The title of my talk is a little confusing or misleading because, in fact, as the first slide says, I am an NVIDIA Cuda fellow, which means that I'm going to represent NVIDIA in this meeting. There are lots of vendors here, as you can see, from HPC. So I have changed my mind, and instead of talking about something that most of you have already heard about and you are more expert on this, I'm going to focus, as I said, in the new things and technology that NVIDIA has developed. So if you see the talk outline right here, so, as I said, I will try to go much faster with all this stuff and leave more room to explain more details about the hardware features of the new graphics cards that NVIDIA has developed, in particular the Kepler and few things about the Echelon 2. Right? So, with this intention, I think that we all will have more fun. Okay. Talking about, in general, about what is heterogeneous computing, in fact, you know that you can favor CPUs or GPUs depending on the nature of your application, right? So if what you have is something that favors task paradigms or intensive I/O, your guy is the CPU, right? And then you try to combine things with files and try to balance the execution through the nodes and everything, and also balance the I/O concerned on each of the devices. On the other hand, if you have something that contains more data paradigms, you know that you are more akin to GPUs. So basically, you try to express things using data paradigms, and hopefully you have large scale as well. This is a very good friend as well. But in most of the cases, or most of the case, or the times, what you have is a hybrid model or heterogeneous model in which you have part of each of the piece of the cake. And in this case, you have to apply things coming from both ideas. So things are coming more demanding from the application and the programmer's perspective. And what you have is, you have two different things. I call the mountains and the beach, right? Because here in Malaga, in South Spain, we have mountains, we have beach, everything at hand, right? So you cannot compare the beach and the mountains. The beach is this, and the mountains are this, right? They are just different. People like more mountains. You go to Sierra Nevada, which is 100 kilometers away only, right? You want the beach to stay here with us, with NVIDIA in this case, right? But you can compare both. And the good thing is that it doesn't matter what kind of customer you are. If you come in favor of the mountains, we offer you a hotel in the mountains. If you want to come to the beach, we offer you a hotel in the beach, and everyone is happy, right? So all you have to know is what the beach is about and what the mountains are about too, right? Another thing is that you can be, if you go tourist, right, you can be a poor guy, you can be a decent guy, or you can be a rich guy, right? Depends on. So there are a bunch of poor guys like here, right, like me, or you can be a large-scale lateral touring, which you spend much more budget, and there are few less guys like that, right? So there are like three different levels with the cluster right in between. Few words also about the GPU evolution to connect afterwards with what I'm going to say about the new platforms. The good thing that not many people can talk about when you are talking about HPC is money and revenues, right? So GPUs are everywhere, and you know all these numbers which say that there is money behind it, which is actually one of the promising things about it. You make money with GPUs. That's why they are going to be there. I don't know if forever, but they're going to stay with us, like the rock and roll, right? So another thing is that, as you can assume, this has been deployed an extraordinary evolution over the past 5 years, concerning the number of papers you see in conferences, the number of universities that are teaching, the number of GPUs that are out there, the number of active programmers that are working with that, the number of compiler downloads, which are skyrocketed right now, the model is pretty much everywhere, right? So not much to say about it, but everything has been basically deployed in 3 different phases. This was the model that I was learning when I was studying here in the university, my computer science career, right? Then when I started working on GPUs, it was like this. So you had to learn how to render the graphics and then try to disguise your application depending on rendering terms, which were very unlikely for you to know, right? Like textures, like vertices, pixels, positions, resolutions, many things you were not expert of. And at the end, you combine the good things of these 2 models into what is Cuda, which means that try to avoid people to know what a vertex is, what a pixel is, what a texture is, all this stuff, right? And that's what we are right now, so hopefully we are trying to combine both things in a nice way. And how do you connect these things to programming trends? So basically you have here the 3 execution models, so you have what the GPU is offering you, and also with the CPU is also offering right now, which if you can have a little detail here, I am focusing or strengthening on the vectorizing things, because in my opinion it's one of the things that the CPUs have to offer us compared to the GPUs bandwidth and the gigaflops and all this stuff. You are also aware that the OpenCL is out there, so I have taken borrow those numbers from Simply Higher, trying to show you the evolution of both Cuda and OpenCL. I don't think they are so rivals, but maybe friends, but this is the tendency of the chances for you to get a job. If you are a good Cuda programmer, which is the green line, or you are a good OpenCL programmer, which is the blue line, right? So you think you have goods and odds on each of the stuff, right? We are like here right now. I don't have this up to date, but looks like that this is coming interesting, because now we are like in the crossing border, more or less, right? So I think they are both going to survive. So I'm not going to stand up on my opinion of which one is going to be best or worse or whatever, just to show you that they are both sharing the marketplace right now. In the programming point of view of my talk, I'm going to summarize just brief things, just to focus more on the hardware, as I said at the beginning. So few words about libraries. So when a guy comes to me here, a student comes to me for me to write the PhD or the master thesis or something, the very first word I say to him is, go to Google. Go to Google and try to figure out if the things you have in your mind to implement on GPUs is already there. Because there are many codes that people allow you to use. There are many math libraries, many things. So this is just a shot of what you can expect to find there. So many of them have been developed by NVIDIA, by the company already, but there are many others that are not done by NVIDIA. And this is one of the good things also about GPU computing, and this is almost everywhere, and there are, as we saw, many programmers, and there are very few things that are done by NVIDIA, and there are a lot of other things that you can borrow from other generous guys that have already done the job before. So it's pretty much punishing you what you figure out that you have spent a whole summer time developing something that someone has already done before you, and also much better than you, right? So it's better to stop this. And what if you want to change the platforms? That's few words also about this, right? Because the global picture also shows you all these alternatives that you got from a Cuda source. So if you are a good Cuda programmer like this, you have basically these 5 choices. So you have let's say the 1.0 version, which is go to the regular path this way with NVIDIA, MVCC, and using some flash, you can also port your code instead of to the NVIDIA GPUs to the CPU multi-core from Intel, from AMD, whatever, right? There is a new enhancement of these things from the program group, which allows you to enhance performance, also going to these 2 target platforms. Then we got the Ocelot here, which is benefits from the fact that the BTX is right there, so it's kind of an intermediate representation of your Cuda code, and allows you to go from the BTX to all these 3 choices you have available. Then if you want to move to the CPU to compare your performance and you start the other way around, which means that you don't start from C and then move to Cuda, but you start with Cuda and then want to see what's going on with your application when you are running that on the CPU, you can go through MCUDA, which tries to do the other way around. Starts from CUDA and the target is the C code, which afterwards you can deploy on each of the CPUs as well. And the final movement is Swan, which goes from CUDA to OpenCL, and using the features of OpenCL as well, you can move underneath to any of these three choices as well. And so you have plenty of choices to move between pieces between heterogeneous computing and play with the game in a very nice way. So it doesn't matter whether you start here, you have at combination level many choices to move across platforms. Playing with integrity, portability, efficiency, performance, and all this stuff. A few words about Ocelot because it's one of the most interesting approaches of this. First of all, it's a dynamic compilation environment for the PTX code, as I already said, and it's evolving very fast. Actually, the very last version comes from April 2012, less than 6 months ago, and it's supporting many different platforms. So this is alive and kicking and working really well. Have a very good opinion of it. Swarm, as I said, is a source-to-source translator, so you have to rely afterwards on any of the compilers, so either the Cuda compiler and the OpenCL compiler, and you can benefit of any of these two strengths. Right? So it's passing from one side to the other side, and I have put here very few things that you can benefit from when you are working using Swan. For example, you can use it to evaluate the OpenCL performance when you have already a Cuda code, or you can reduce the dependency from the MVCC compiler when you first compile the thing, or you can support multiple Cuda compute capabilities on a single binary. You can have a single code, and part of it can be developed in a different scenario. Or finally, also you can use it as a runtime library to manage OpenCL kernels. So it's another useful tool you can use in this kind of heterogeneous computing framework. Then let's go from old to new, right? This is one of the newest, which is the Portland group tools that we in our lab have installed this summertime. So it's very new, and this is not a translator from the source code, but it's working at runtime. So, and at the end of this year, it will also allow you to build a unified binary, which will simplify all the software distribution. So it's going to be much more demanding in this respect. And it has two main advantages, in my opinion. First of all, is the speed, because you don't even need to have a GPU, and also you can use you can vectorize the code on SSS or even in the AVX for a wider vector length. And finally, good news also about this is the transparency, which means that even those applications which are using particularly rendering things like textures and any other graphical resources, you can also port it easily using this tool. Right? So these are also good news concerning. So it's a very demanding tool and quite powerful, and the Portland group is behind it, which is also interesting. But you can also go the other way around. You don't start from Cuda and move to another platform, and you can start from other things you have developed in C, in Java, in any other things, and then you can move into the Cuda world, right? So summarizing, well, this is a lot of information in very few things, but just to summarize, one of the most nicest way to go is to use this concept of proposed interface generators, which is, in few words, a wrapper which allows you to spell things in something that is more familiar to you, and the final name is going to be the Cuda code, right? And you have here a lot of possibilities. So I don't know which ones you are familiar with. I have here highlighted the one like C# and Python or Java, which are the ones that are my favorite. And if you are a more, let's say, math user, you can use even MathWorks or Jacket to go on numerical computing, or also work using the parallel computing toolbox. So these are also many choices, just for you to have a summary of everything that is out there, not to be very specific. The only thing I'm going to be a little more focused, and I have develop 4-5 lines is OpenACC, because OpenACC is very much connected to things we have seen in the past, HPC, OpenMP, and all this stuff, right? So basically, it's a Cuda with directives, let's say, right? So it's the title is Open Programming Standard for Parallel Computing, and the 4 vendors are Cray, the Fortran Group, CAMS, and NVIDIA. You have the standard here, and the idea, I think most of you already know about it, is that let's say that it's an alternative to relax your requirements as a programmer, right? So you are a very naive programmer, you don't know very much about how to program a GPU. What you do is you take the source code coming from the C, which is very familiar to you, and then you put several annotations. So you can start either from C, you can start from C++, or you can start from Fortran, and then you provide some annotations, and with these annotations, you relax the effort of the programmer, but hopefully you will also have some penalty in the performance code. So it's not what you can get is you are a very good programmer, right? So this is basically the idea. The idea is that you have here the code you are familiar with, right? It can be a C or a Fortran code, and then you put here the hints. You say, like the primary regions, say this is a parallel loop, or these are independents, there are no dependencies here, this is a local stuff, whatever you can imagine, you express it the right way, and then compiler does the rest of the job for you. But the discussion is about performance, right? So you can be lucky in the sense that you can have performance increase working for a week, or you can have less performance because you have worked less time, or you can have same performance in less time, right? So this is the ideal scenario you want to work with, and depending on the application and also your programming skills, you'll have different results. But that's pretty much the idea about it. And now, then when I have half of my talk to focus on the hardware designs, particularly on Kepler. So from now on, I hope that I can contribute with something new to you. And if you want to raise me questions at runtime, let's say, please go ahead. Okay. Few words about Kepler. So this is the design of the architecture. It's a many-core but a large scale, which means that you have 15 multiprocessors. And before that, you know that with Fermi, the multiprocessors contain few processors, few cores, few streaming processors, right? Now, in this case, each of the multiprocessors is having 192 cores. So in this case, total is 2,880 cores, right? Almost 3,000, which is large scale compared to the previous generation. That's the very first thing. Just to remind you a little bit about the Cuda execution model, you have three different, let's say, levels in the memory hierarchy. You have the local stack, which is your register, and also the shared memory. Then you have these two intermediate levels of constant and texture cache. And finally, you have the global memory. And here also you have as a thread that you are running to be allocated on each of the streaming processors. You have your local stack, registers, and a local memory from the compiler. You have the shared memory in between, which is shared between the threads within a block. And then you have the global stack, which is the video memory right here at the end. This is in few words what Cuda is about. And these are going to be the difference in the memory hierarchy, comparing what you have or what you are used to, using Fermi on the left-hand side and using Kepler on the right-hand side. So you see that, okay, the real name is going to be video memory. So technology right now is GDDR5, so we are with that, maybe more size, but not very much about it, right? The very first difference to have in mind right now is that the L2 cache doubles the size. So here, if you remember, in Fermi you have 768 kilobytes of memory to share between all cores, and here you have 1.5 megabytes. And the other difference comes in the first level of cache, in which you have this read-only data cache. So essentially, this is, in few words, the texture memory that you have formerly in Fermi, and many wise programmers were able to use it, but now easily reachable, right, from Cuda instructions. So now you have three components in this respect, and the other difference comes, I'll show you afterwards the fine print about this, right? But the other interesting thing is that And you know that in Fermi you can combine this. You have 64 kilobytes for both. It can be 1648 or 4816. Now you can spread it also 3232. That's a question many people has raised recent over the past years. So why you don't allow to have 50-50, which is the fair thing, right? So now you have this third choice as well in this partitioning of these two guys. So I have collected or summarized the whole picture in this table. Basically, as you can see, I have put the two generations of Fermi and the two generations of Kepler. Right now, we are here. These are the cars you can buy right now, the GK104. And as you will see, this is not the true Kepler machine. The very strong, the good one is this one, which is going to have full coverage of what Kepler architecture is about, right? But concerning the concept of Cuda compute capabilities, you have 2.0 in the first version of Fermi, 2.1, and then 3.0, sorry, and 3.5, right? So number of processors is going to be 512 with 16 decomposes into 16 multiprocessors, and in the very last end you got 2880 and decomposed, as we saw in the first picture, in 15 multiprocessors, right? So let's go ahead, and we have here, let's say, what is the software constraint, right? So after deploying the number of cores that you have for each multiprocessor, that I have already anticipated it was 192, you go to the warp size, which is going to keep constant through the whole generation right now. And then you have a little increase in the number of warps that you can allocate per multiprocessor, and also in the number of red blocks that you can allocate per multiprocessor. So you are doubling the size here and almost doubling here as well. You keep this one constant, and for the number of threads that you can run simultaneously on each of the multiprocessors, you have also increased to 2K. Right? So right now it looks like that these two guys are one bag, and these two guys are another bag, right? But there are few secrets still to tell you about this, which are these ones, right? So now what you see is that, okay, the number of registers per thread increases dramatically, is fourfolding in the new version of the Kepler architecture, right? For the registers, you are doubling the size, and for the shared memory, I also anticipated that you can partition into 50-50, right? Not only 1648 or 4816, but also 3232. So it's the same size, but you have more freedom to spread things about. And the final thing, after this one, which is the problem size that can also be increased using the much higher grid dimensions, which is good news when as far as high performance computing or large scale applications are about, which is what this conference is about too, is these two features. Oh, there's a little. Oh no. Okay, I will tell you what this is about. This is hypercube, okay? Not hypercube, but hypercube. Hypercube. I have developed a couple of slides for this and another couple of slides for this. So I will explain you right now what these two features are about. But these are the more dramatic changes concerning the architecture, or more specifically concerning what the architecture can be dealing with concerning your software or your program, right? Let's go with them. The very first thing is dynamic parallelism. What is that? So now the GPU can create its own work. You are not the slave of the CPU anymore. You can create dynamically your own thing. So depending on the values of your application, you can decide, as a GPU, I have the right to start new threads, new blocks, new jobs with me, right? And that's what you can do. So the scheduling, this complexity is going to increase dramatically, and also the perspective of your application, because now concerning the regular field, these are very good news, right? So here is an example about it, right? You start computing and then you say, okay, because I don't have in Fermi the chance to decide how to move or how to create things at runtime, I start with these conservative things. Very bad. Why? Because there is no work in this time, and there is plenty of work here, right? So the other thing is, okay, I'll be more aggressively at compile time, right? And then you can go this way. But again, this is too fine. So what is the right thing to do? The right thing to do is, depending on the value you find when you are starting your application, then you start recursively increasing new jobs into your block of static things you started before, right? So that's one positive thing we're going to see affecting Cuda performance and GPU applications from now on. And the other thing which was missing in the last row of my table was the hypercube. What is a hypercube? Well, maybe you figure out that with dynamic parallels, what happens is that the interaction between the CPU and the GPU is very strong, which means that before that the CPU was shipping things around to the GPU, and the GPU was shadowing things which were shorted on a queue, right? But now this is not true anymore, because dynamically the GPU can also increase the size of the queue, right? So if you are sending jobs, then you don't know how big they are going to become when they are computing, because as long as you are starting the execution, then you can grow, and then it's going to be very unbalanced, everything, right? So what you do is, you allow the CPU and the GPU to communicate in a very different manner. So concerning MPI tasks, you can start doing many things dynamically and executing all at the same time in the GPU. So you can create many streams and ship all the streams to the GPU, and they are not going to keep the order of the execution as they were doing before, right? So this is an example about it. Let's say that we are in the Fermi model and we were executing things coming from 3 different streams, right? So essentially, these 3 guys are parallel, right? Which means that there's no need for you to start executing Q after C, right? Because here in this conceptual model, structural model, Q can start before C is over, right? But the way it was implemented was this, which means that there is a chain here, there is another chain here. So you start with ABC, and until C is over, you're going to start P. Maybe you can overlap a little bit if you are a wise programmer, the end of C with the beginning of P, right? But you cannot start Q after C is over. That's impossible in the Fermi model. But this parallel execution allows you to go that way, right? So what you have in Kepler is something like this. So now you have 3 different queues, and the GPU is following things in a very undeterministic way. So you don't know actually in the Kepler model whether Q is going to be executed before or after C, right? So you have much more flexibility, freedom to schedule all the resources, and for all the applications that require this freedom, the performance is going to boost. And the very last slide is about echelon. I didn't want to bring this one, but I hope I have time. In fact, I have 3 more minutes, right? So I can put this last slide, because it's connected very much to the very nice talk that DK Panda has given us at the very beginning of the meeting. Because there are a lot of concepts that he has already presented early in the morning. So the echelon is the successor of Kepler. Echelon is going more or less to be intended to appear in the market around, I expect, 2015 maybe. And this slide was presented by Bill Daly in IPDPS 11, so it's from last year, but shows you what a flavor of what the company is working about, right? So here you can see that there is a global space. So many people have talked about it in the talks. You can see that there are message passings. Also, there is a memory hierarchy, and there are many things also that we have enriched our mind with in the past today, which are collective operations and block transfers, messages. So let's say that with this, what you can see or you can imagine is kind of convergence between what you already have in mind and what Cuda is offering, right? And that's the end. Thanks so much.